Hello, in this video I'll try to explain you that how you can use a STM32 with a LCD display and to use a current sensor to measure the current of the load and with a overload or you can say overcurrent relay protection. So in this video as you can see that I am using LCD 16 cross 2. It's mean it has 16 in row columns and 2 you can see it has rows, and which is connected with a variable resistor to control the brightness of the LCD. And over here we have basically used a LED. You can also use some kind of relay with which you can show the trip, but I am using a LED over here to show you the trip status. So this is the 220 volt source with a variable resistor to vary the load to check the accuracy of the current. We are using a 220 volt load with a AC ampere meter to check the you can see the accuracy of our sensor and the code. And this is the current sensor, which is ACS 712 30 ampere sensor. This is a variable you can this is a voltage divider resistor, and we are using a STM32 F103C6. You can use any kind of STM32 controller with the same code but little bit of changes. And over here is a oscillator. So what should we do now is that we should run the simulation. So as you press the run button, you will see that the LED's light will turn on, and it will take a little bit of time. Okay, and the reason for that is we are running this simulation in the software, and the software is not running in real time due to excessive CPU load, so that is why it takes a little bit of time. But on the real hardware it will be instant. Okay, as you give it the power, it will start. The on the real hardware, the values or you can say the controller will work in real time, but a simulation takes a little bit of time. Okay, so it is saying that this is the millisecond time for the trip. As you can see that we are within the range. The current is 0.4343 amps, and you can see 0.43 amps. Okay, but 00 volts, as you know, we are, as you can see that we are not basically measuring the voltages. So it is 0.43 amps, and the ms, it's millisecond time for the trip. This is infinite. It's mean that there will be no, you can say, there will be no tripping because the current is within the limit, so the time for the trip is infinite. Okay, so as we decrease the current, sorry, as we decrease the resistance to increase the current, you can say it is now 0.74 something, and this will also change to 0. It will take this is the reading it has taken in the previous cycle, but it will update it. Okay, it just take a little bit of time. Okay, so now you can see that it is about round about 0.74 or 0.75. so it is, you can see that 0.74 or 7.5. so it's just, there is a little bit of marginal, you can say, the error. Okay, so now if I just make it to this very maximum, okay, so the load has gone to its full status. Okay, you can see it's just will take 0.21 millisecond to trip the system, and it's also showing that the system has been tripped. The first thing it has done is trip the system, and after that it will display the values. Okay, so it is designed to trip the system instantly, okay, without even displaying the values, so that to make sure that there is very to make sure it is doing its job. So its first priority is to trip and then display. So you can see it is 0.24.70. You can see it is at 24.7 or 20. It's little bit of fluctuations. Okay, and over here the red light has turned on to show you that the system has been tripped. Okay, so this is how its complete circuits looks like. Okay, you can also drop it to the 6%, and you will